Good morning, everyone, and welcome to our comprehensive lecture series on biochemistry. Today, we are embarking on a fascinating journey into the world of essential nutrients uh, that are the very foundation of our physiological processes, minerals and trace elements. As we begin, let's understand what we mean by a mineral in the biochemical sense. A mineral, from a nutritional and biochemical perspective, isn't just a shiny rock. It's a chemical element that meets several strict criteria. It must be naturally occurring, means found in the earth crust. Second, stable at room temperature. It doesn't decompose under normal conditions. Number three, represented by a chemical formula. So it has a defined atomic structure. Number four, they are mostly or usually abiogenic. This means it's not derived from living organisms, though it can be incorporated by them. Number five, ordered atomic arrangement. Its atoms are arranged in a specific repeating pattern. Now, why are these elements are so critical? They are not just passive passengers in our body. They perform several vital functions that are absolutely essential for our very existence. Think of them as the silent workers behind the scenes. They are involved in calcification of bones and teeth, blood coagulation, neuromuscular irritability, acid-base equilibrium, fluid balance, osmotic regulation. So, without these minerals, life, we know, it would simply not be possible. Now, let's discuss the classification of minerals. Because our bodies require them in vastly different amounts, we classify them into two main groups. First, we have the macro minerals, as known as principal elements. These are the minerals we need in large amounts, greater than 100 milligrams per day. The major minerals here are the calcium, phosphorus, magnesium, sodium, potassium, chloride, and sulfur. We will be covering most of these in detail. Second, the microminerals, the trace elements. These are required in amounts less than 100 milligrams per day. Don't let the small quantity fool you. Their importance is just as immense. This group includes iron, copper, manganese, zinc, molybdenum, selenium, and fluoride. Now, for the sake of completeness, the lecture notes also mention a few other categories. Minerals that are necessary but whose functions are not fully known, like chromium, nickel, non-essential contaminants, and a very important group, the toxic minerals like aluminium, lead, cadmium, and mercury, which we must actively avoid exposure to. This sets the stage for our very first and arguably the most abundant macrominerals, the calcium. Let's talk about calcium, right? It holds the title of the most important and the most abundant mineral in the body. Think about it. The total content in an average adult is a staggering 1 to 1.5 kilograms. Where does almost all of it go? A full 99% is stored in our bones and teeth, giving them their rigidity and strength. The remaining 1%, although very small quantity or the amount, is arguably the most dynamic and critical fraction. It's found circulating in our blood and within our cells. And it's this 1% that governs the life sustaining functions we just mentioned in our previous slides, right? Now, a critical question for you. Where do we get this essential mineral from? Let's look at the sources. Without a doubt, the best source of calcium is milk. Cow's milk provides about 100 milligram per 100 ml. It's a perfect package, often combined with the ideal ratio of phosphorus for absorption. We have medium sources like egg yolk, beans, and leafy vegetables. And then we have poor sources, which is a crucial point for many in South Asian countries. Cereals like wheat and rice contain only small amounts of calcium. When these form the staple of the diet, the risk of calcium deficiency becomes a very real concern. So we get calcium from our diet, but how does our body actually get it from the food we eat into our bloodstream and bones? Let's explore the intricate process of absorption. Calcium and absorption is not a passive process. It's a highly regulated, active transport mechanism that takes place primarily in the first and second part of the small intestine, the duodenum. It requires energy and a specific carrier protein helped by an enzyme called calcium dependent ATPase. Let's break down the factors that influence this absorption. Factors that increase the absorption. The very first one is vitamin D. This is a single most important factor. The active form, calcitriol, acts like a key, turning on the genes that provides a calcium carrier protein called bindin, right, inside the intestinal cells. Without adequate vitamin D, you simply cannot absorb calcium efficiently, no matter how much you eat. The second one is the parathyroid hormone, the PTH. When blood calcium levels drop, the parathyroid gland releases PTH. PTH doesn't act directly on the gut. Instead, it goes to the kidneys and tells them to active more vitamin D, which then does the job. Number three, the acidity. An acidic environment in the gut helps keep calcium in its soluble and absorbable form. Number four, the amino acids like lysine and arginine can also enhance calcium uptake. Now, what factor decreases or hinders calcium absorption? The very first one is the phytic acid, found in the bran of cereals. Phytic acid binds calcium, forming an insoluble salt that we simply excrete. Good news is that fermentation and cooking can significantly reduce the phytate content. Number two, oxalates. Oxalates present in leafy vegetables like spinach. Oxalates also form insoluble calcium oxalate crystals. So while spinach is a good source, its calcium isn't as bioavailable as the calcium in the milk. Number three is the malabsorption syndrome. Some conditions where fats aren't absorbed properly, like a celiac disease, leads to the formation of insoluble calcium soaps with fatty acids. Number 5, high phosphate levels. An excess of phosphate in the diet can cause calcium to precipitate out as calcium phosphate. The ideal ratio of calcium to phosphorus for optimal absorption is between 1:2 or 2:1, a ratio perfectly balanced in milk. To summarize the absorption process, calcium is absorbed in its inorganic form, mostly by active transport in the proximal small intestine, and to a lesser extent by passive diffusion in the distal parts. Low body stores and the presence of protein and bile salts can increase absorption, while the process unfortunately becomes less efficient as we age. Now, once absorbed, calcium doesn't just sit around, it gets to work. Let's look at its remarkable functions. The function of calcium as are vast and they can be broadly categorized. The structural functions. The calcium obvious is the development and maintenance of bones and teeth. Our skeleton is a dynamic calcium reservoir. Osteoblasts are the bone building cells that deposit cells, while osteoclasts are the remodeling cells that break down bone to release calcium back into the blood when needed. This is a constant balancing act. Second function, regulatory and signaling. This is where the 1% of the calcium outside the skeleton shines. The very first one is muscle contraction. Calcium acts as a trigger. It binds to the protein called troponin C, which unmasks the active sites on the actin filament, allowing the muscle to contract. A deficiency of calcium can lead to uncontrolled muscle spasm, known as tetany. Next is the nerve transmission. Calcium is, Calcium is essential for the release of neurotransmitters from the presynaptic neuron to postsynaptic neuron, allowing nerve impulses to be transmitted across the synapse. Next is the blood coagulation. Calcium is known as factor 4 in the coagulation cascade. It acts as a cofactor binding to proteins like prothrombin to help to form the clot. Next is the enzyme activation. Calcium acts as a second messenger. It binds to a protein called colmodulin, and this complex then goes on to activate a vast array of enzymes, including protein kinases, phosphorylases, or kinases, and many other involved in metabolism and cellular functions. Next is the hormone secretion. Calcium mediates the release of key hormones like insulin, parathyroid hormone, and calcitonin. Next is the heart function. It is critical for generating the electrical impulse that initiates the heartbeat. So calcium role is so fundamental that its levels in our body must be tightly controlled. The normal total calcium in blood is about 9 to 11 milligram per deciliter. However, not all of it is active. Calcium exists in three forms in the blood. The very first one is protein-bounded calcium. That is non-diffusible. About 4 milligram per deciliter is bound to proteins, primarily albumin. This form is inactive and cannot be used by cells. Second one is ionized form, that is diffusible form. About 5 milligram is the free ionized form. This is the physiologically active form. It's this level that the body works so hard to maintain. If the ionized calcium falls below 4.3 milligram percent, tetany can occur. The third form of calcium is the complex form, that is again a diffusible form. About 1 milligram per deciliter is bound to small anions like citrates and phosphates. Now, how is this delicate balance maintained? By three key regulators. The very first one is vitamin D, the calcitriol. Its primary role is to increase blood calcium. It does this by increasing calcium absorption from the gut, increasing calcium reabsorption from the kidneys, and stimulating osteoblasts to a degree, but more importantly, working with PTH, parathyroid hormone, to mobilize calcium from the bones when needed. Second one is the parathyroid hormone. When blood calcium is low, parathyroid hormone is released. It acts in three ways. It stimulates the kidney to activate vitamin D. It increases calcium reabsorption in the kidneys. And it directly signals osteoclasts in the bone to break down bone matrix and release calcium and phosphate into the blood. The third one is the calcitonin. This is the antagonist to the parathyroid hormone, released from the thyroid gland. When calcium is too high, its job is to decrease blood calcium by either inhibiting the activity of osteoclasts, thus reducing the bone resorption, or increasing the excretion of calcium by the kidneys. And a crucial clinical point is this: there is a reciprocal relation with phosphorus. Their concentration in the serum are often inversely related, and their product, calcium into phosphorus, is in normal adults is around 40. Finally, we must consider what happens when this regulation fails, leading to either hypercalcemia, that is too much calcium, or the hypocalcemia, that is too little calcium in your serum. Let's discuss the hypercalcemia, when the blood calcium level is more than 11 milligram per deciliter. Can be caused by a range of conditions, most notably the hyperparathyroidism. Next is multiple myeloma, Paget's disease, metastatic carcinoma of bones, thyrotoxicosis, the Addison disease, benign familial hypercalcemia, the dehydration, prolonged immobilization, tuberculosis, leprosy, sarcoidosis, milk alkali syndrome, some of the drugs or the chemicals like drugs, thiazide diuretics, excess vitamin D intake, and vitamin A intake, and even the excess calcium given intravenously. And the theophylline is also responsible for the hypocalcemia as well. Now, let's discuss the hypocalcemia. Hypocalcemia when the calcium levels are less than 8.8 milligram per deciliter. And the causes may include deficiency of vitamin D, deficiency of parathyroid hormone, increased calcitonin, deficiency of calcium itself, increase in phosphate levels, phosphorus levels, and hypoalbuminemia. What about the excretion of calcium? Out of 500 milligram of calcium taken orally daily, 400 milligram is excreted in stools, and the remaining 100 milligram is excreted through the urine. Excessive sweating also results in an appreciable loss of calcium from the body as well. Is there any chance of toxicity if calcium is taken in excess? Calcification of different soft tissues of the blood of the body occur, like the aorta, renal arteries, leading to the severe malfunctioning of such as the structures of the body, right? Now, let's discuss the calcium deficiency and its daily requirement, right? So what happens if we don't get enough calcium over a long period? We see rickets in children, leading to soft, weak, and deformed bones. Osteomalacia in adults, where bones become soft due to poor mineralization. And osteoporosis, a condition of porous and fragile bones, is often the culmination of decades of net calcium loss, especially after the age of 40 to 45. This is why, after the age, the recommended intake increases to 1500 milligram per day plus vitamin D intake. What are the daily requirements or the RDA, recommended daily allowance for the calcium? The RDA for an adult is 500 milligram per day, but this is considered as minimum. For a growing child, it's about 1200 milligram per day. During the crucial periods of pregnancy and lactation, the requirement jumps to 1500 milligram per day to support the developing baby and milk production. So, to recap, the calcium, it is the most abundant mineral with 99% is in our bones and teeth. Its absorption is a tightly regulated process dependent on vitamin D. Its function is everything from bone structure to muscle contraction and nerve transmission. Blood calcium levels are meticulously controlled by a trio of hormones: the parathyroid hormone, vitamin D, and calcitonin. And finally, a deficiency can lead to bone diseases, making adequate intake throughout life a cornerstone of health. So this is a comprehensive overview, lays a critical foundation of our understanding of calcium. In our next lecture, we will continue our exploration of the macrominerals, delving into the intricate world of the phosphorus and the other minerals, its intimate relationship with the calcium, and its vital role in energy metabolism. Thank you for your attention. Please feel free to leave your questions in the comments below. And don't forget to like and subscribe for more in-depth lectures for biochemistry. Thank you once again.